Hello sir, I am Arko Datta, a student of Kojivar Government Engineering College from EC department. My roll number is 34900324023. Here's the project you have given us. So let's start. In this video, we are experimentally verifying the sampling theorem using two-tone signal. We will examine its behavior when sampled above, at, and below the Nyquist rate, and then reconstruct it using a custom sync interpolator to see the effects. So here you can see that our test signal shown in cell 4 is a two-tone composite, a 5 Hz tone and a 22 Hz tone. This setup lets us observe how both lower and higher frequencies react to different sampling conditions, especially focusing on the 22 Hz tone. So the sampling theorem covered in section 1, here you can see the sampling theorem covered in section 1 states that to perfectly reconstruct a signal, the sampling rate here you can see must be strictly greater than the twice the highest frequency. Here you can see the mathematical explanations. Here it is. Here you can see Fs is greater than 2F max. So we can say that the sampling theorem covered in section 1 states that to perfectly reconstruct a signal, the sampling rate must be strictly greater than twice the highest frequency, also known as the Nyquist rate. If Fs is too low, we get aliasing, where high frequencies incorrectly appear as lower ones, making reconstruction impossible. Here you can see no receiver can undo this. Here the imposter frequency is indistinguishable from a genuine tone at F alias. No receiver can undo this. And reconstructions ideally uses sync interpolation. Here we can see our reconstructions. Here's a sync interpolation. It's ideally uses sync interpolation. We can see the equation for that. Here we can also see the critical case where Fs is equal to 2F max. The theorem requires a strict inequality with Fs is equal to 2F2. The sample instants are Tn is equal to n by 2 F2. So 0.5 sine 2 pi F2 Tn equals to 0.5 sine pi n equals to 0 for every n. The high tone is sampled exactly on its zero crossing and vanishes from the record. This is the sampling phase sensitivity that makes the Nyquist rate unusable in practice. And there is also error matrix, which is ms is equal to 1 by m summation xrtm minus xtm whole square, where rmsc equals to root over msc and e infinite is equal to max in mod xrtm minus xtm. Oh, especially not mod, sorry, infinite equals to max of xrtm minus x of tm. Yes, Here, from cell 4, our maximum signal frequency is 22 Hz. So the Nyquist rate is 44 Hz. We are testing three sampling cases. Case A, above Nyquist at 220 Hz. Case B, at Nyquist at exactly 44 Hz. And case C, below Nyquist. Here all the cases you can see at 30 Hz, where aliasing is expected. So, in case A, where it is above Nyquist analysis. For case A, figure 1 shows dense samples for fs is equal to 220 Hz. In figure 2, confirms faithful reconstruction with a low NRMSE of just 1%. Figure 3 spectrum. Here's the figure 1 which we have talked about, and in the figure 2 it confirms faithful reconstructions with a low NRMSE of just 1%. Here's the figure 2 talk now, and in figure 3 spectrum clearly shows only the original 5 Hz and 22 Hz tone with no aliasing. The small error is due to our finite truncated sync. Interpolator. Finite truncated sync interpolator as explored in cell 9. Now, for case B, sampling at exactly f is equal to 44 Hz. Here, figure 1. Let us see the figure 1. Here, in the figure 1, for case B, reveals the 22 Hz tone is sampled at 0. The 22 Hz tone is sampled at its 0%, essentially disappearing. This leads to a highly distorted reconstruction in figure 2. Here you can see the figure 2. Here we have the distorted reconstruction with NRMSE at 44.5%. Figure 3 spectrum confirms the 22 Hz tone. The 22 Hz tone, here's the 22 Hz tone, is completely, here you can see it's completely absent here. This demonstrates why Nyquist rate is a theoretical boundary, not a practical design point. Now in the case C, first of all we will look at the cell 4 for that. Yes. For case C, below the Nyquist rate analysis, at f is equal to 30 Hz, figure 1 shows sparse. Here the figure 1 which shows sparse here, and distorted samples. In figure 3, the 22 Hz tone has aliased down to 8 Hz. Here it is aliased down to 8 Hz, perfectly matching our theoretically theoretical prediction in cell 11. Here's a cell 11 we can see. Here's a cell 11. We can see that it matches the mm, theoretical prediction in cell 11. Theoretical alias frequency worked out explicitly. Here is the code and the output. Nyquist, here you can see. At Nyquist, here you can see, and below Nyquist, here you can see. It has become 8 hertz here. Now, figure 2. We will look at figure 2. Figure 2 shows an extremely poor reconstruction with 63% NRMEC. This is the wrong signal. Here is the wrong signal. Aliasing has irreversibly corrupted the data. So the summary, in essence, we have verified the sampling theorem, sample above Nyquist for accurate reconstruction. The strict inequality where f is greater than 2f max is critical, aliasing in predictable and irreversible, meaning once it happens, the original information is lost. This highlights the need for anti-aliasing filters before sampling. Finally, in cell 17, so we will look at the cell 17. Okay. Finally, in cell 17, provides automatic validation. Our results show 6 out of 6 checks passed. Here, all the 6 checks are passed, confirming that our experimental findings perfectly align with the sampling theorem's principle. This experiment clearly illustrates the fundamental importance of correct sampling rates and anti-aliasing techniques for accurate digital signal processing. Thank you for watching.